Hello, Calc 1 friends. Today we are going to begin Chapter 5, Integrals. First section in Chapter 5 is understanding area when it comes to calculus. Our goal is to compute the area between a curve and the x-axis over a given interval from A to B. So we are interested in this area. We're going to estimate this area using rectangles. If f of x was a nice shape, perhaps a diagonal line or maybe a horizontal line, we could use geometry, but for most functions that's not going to be the case. So what we're going to do is divide this interval up, the interval from A to B, into equal subintervals, and then we're going to create some vertical lines. And then we're going to, from these vertical lines, we are going to create rectangles. We can use either what we call left rectangles by going over the first subinterval and going up the left side and using the left side to determine the height of the first rectangle. So this would be an example of a left rectangle, and we can see that the area in this rectangle is pretty close to the area between my hand and A under the curve. We can use a right rectangle. So if we have this rectangle right here, we're between this interval, we can go up the right side to determine the height of the rectangle. So there would be an example of a right rectangle, and we would use this area. Or we could use what we call a midpoint rectangle. So if we're looking at this base for this rectangle right here, we would literally go up the middle to determine the height of this rectangle. And this time we'll have a little bit of area over and a little bit of area under, which will give us a pretty good estimate. So when we're estimating the area under a curve using rectangles, we usually choose one of these three methods. We'll usually go with all left rectangles, all right rectangles, or all midpoint rectangles. So the best way to see what's going on here is to do an actual example. So let's look at a simple problem. Let's estimate the area under the curve f of x equals x squared over the interval from 1 to 5 using 4 rectangles. So I'm interested in this area right here from 1 to 5. Now notice my scale, I scaled my axes so I could get the whole picture into the graph. All right, so we're looking for this area right in here. It says to use 4 rectangles. Now I chose 4 accordingly so that when we divide the interval from 1 to 5 up into 4 intervals, each of the bases of my rectangle will be of width 1. So I'm going to break this up into 4 subintervals. So we're looking at the area from 1 to 5. So if I use 1 as the base of each, or width 1 is the base of each of my rectangles, I will have them at perfect increments of the integers. All right, so we're going to use 4 rectangles. Let's first decide on left or right sums. I'm going to do left sums first. So a left sum. And we usually abbreviate it with an L. And then we use a subscript to determine how many rectangles we use. So this is telling me I'm creating a left sum with 4 subrectangles. So to determine the height of each rectangle, I look at each little subinterval. So there's my first subinterval, and I'm going to go up the left side. So here would be my first rectangle. So the left side was determined by the left endpoint of the first subinterval. So the height is the y value at that point. Now remember, this is the function f of x equals x squared. So the height right here would be 1. So this is a 1 by 1 rectangle. So my first rectangle would have area base 1 and height 1. I'm going to add to that the area from the second rectangle. So here's the base of my second rectangle between 2 and 3. I'm going to go up the left side of the base. So I'm going to use the left end point 2, and I'm going to go up where that meets the curve, and that's going to determine the height of the second rectangle. So remember, we plug this left end point into the curve to get the height of the second rectangle, which would be 4. So this second rectangle right here would be a 1 by 4 rectangle. And we're going to keep going. We're only going to do this with 4. The base of my third rectangle will be the line between 3 and 4 on my x-axis. The height is determined by going up the left side of that third subinterval And the height right here would be determined by plugging in the left endpoint, and that would be a height of 9. So my third rectangle has area 1 base times height 9. We'll continue with this process. Whoops, let me draw that rectangle. And then my last rectangle I'm going to use as a base, the line between 4 and 5 on the x-axis. We're going to use the left endpoint to determine the height of the fourth rectangle. We're going to go up to there, and the fourth rectangle will have height 16 because I plug it into that function. So it will be 1 times 16. So this, let me use a light color. Let's see, so this, we're using this area to estimate the area under the curve. So notice we're missing a little bit. So in this particular case, the area under the curve using left rectangles is going to be an underestimate. So if you add 1 plus 4 plus 9 plus 16, you get an area of 30 units squared. We don't know what the units are, so we're not going to even put them in there. So that's how we would find a left sum. To find a right sum, actually, I drew another page. I have another picture so we don't get too overwhelmed on the same picture. So let's try a right sum over 1 to 5. So from 1 to 5 again. But this time we're going to find the right sum. So right sum n equals 4. So we're trying to estimate this area in here. So the right sum using 4 subintervals. Well, here's my base of my first. Actually, let me draw these in. So I'm going to draw lines between 1 and 4 all the way up to the curve. Remember, this is the function f of x equals x squared. So the first rectangle will have base 1, but the height this time is determined by going up the right side. So right now we're looking just at this guy. Right here, we're looking just at this. And to determine the height of this rectangle, we use the right side of the rectangle, and however tall the right side of the rectangle is. So this would be the first rectangle by using a right sum. The second rectangle, I'll put in the values in a minute, this would be the base and would go up the right side, and where the right side meets the curve, that's going to determine the second height of the second rectangle. So forth and so on. So this would be my third base, go up the right side. This would be my third rectangle. So notice when I do right sums, I go up the right side of the interval where that meets the curve, and then I head left until I'm 1 unit over. So that's what my right sum would look like. So my first base is 1. My first height is determined by the output at the function 2, so it will be 4, plus the second base times the height at the right endpoint. So this one will be 9. This one was 4. The third rectangle has height 16. And the last rectangle has height, oops, I'm a little off there, but 25. So now if I use this area to estimate the sum, we can see that it's a little too much area, but it's still going to be a pretty good estimate. So this area is going to be, if we add 4 plus 9 plus 16 plus 25, we get 54. So I know the area is a little more than 30 because we can see from our rectangles, our left rectangles were an underestimate. My right rectangles were an overestimate. So the actual area is somewhere between 54 and 30 units squared. So I know that's a pretty wide range. We would get more accuracy if we took more rectangles, but it gets a little tedious to do by hand, but you'll see in your homework, you'll have somewhere you have to do some more rectangles. Yeah, it's like if we did 8 rectangles, I hate drawing on my nice picture, but if I did 8 rectangles, it would look like this. Right. So I'm going to just try to do it in a different color. If we did 8 rectangles and we went up the right side, here would be my first rectangle. Here would be my second rectangle. If I went up the right side, that would be my third. That would be my fourth. So you can see we'd be eliminating some of this extra area. And we would get a more accurate representation of the area under the curve. So the more rectangles you use, the more accurate your area under the curve, the estimate of the area under your curve is going to be. Now I had also mentioned midpoints. So a midpoint sum is we're going to use M4. So to find a midpoint sum for the area under the curve, f of x equals x squared. I'm going to still do this, right? But this time I'm going to use, so M, a midpoint sum, we'll use the abbreviation M4. All right, well, the base is still from 1 to 2, but to determine the height of the rectangle, we're going to go right in the middle, and we're going to use that value to determine the height of the rectangle. So this first rectangle, the top still stretches between 1 and 2, but its height is determined by 1.5. So the height of the base of the first rectangle is 1, and the height is 1, whatever the value of 1.5 squared is. To determine the second rectangle, the base is still 1, and then we're going to use 2.5, and where that meets the curve is going to determine the height of the second rectangle. So between 2 and 3 is 2.5, and to find the height, we'd put 2.5 into the given function, so 2.5 squared. Go between 3 and 4, it'd be 3.5. We'll be determining the height of the next rectangle. So the base still stretches between 3 and 4, but the height is determined by the midpoint between 3 and 4, which is 3.5. So the third height is 3.5 squared. And then the last height would be, the base is still 1. The height will be determined by 4.5. Go to where that meets the curve, and it would be 4.5 squared. And I didn't add that one up yet, so let's do this right on my calculator. 1.5 squared plus 2.5 squared plus 3.5 squared plus 4.5 squared, and this gives me 41. So the left sum said the area was greater than 30. The right sum said it was greater than 54. And the midpoint sum says that this area, now notice it gives us a little extra area and a little bit too much area, so it sort of balances each other out. So this is a pretty good approximation of the area under the curve. So to get better estimates, we would use more subintervals. So the notation here is the hardest part. So now let's see if we can write this in mathematical notation. So in general, the area of a region that lies under a curve, f of x, over the interval AB is the limit of the sums of the approximating rectangles. So what does that mean? That means we would find the area using 4 rectangles, and then we'd find the area again using 8 rectangles, then maybe 16, then maybe 100, then maybe 1,000, and we would see that those rectangles would eventually start to look exactly like the area under the curve. So in theory, we would be taking an infinite collection of rectangles. So the definition, the area of a region that lies under the curve, so this is the area we're looking for or interested in. We'll call it area A, is the limit of the sums of the approximating rectangles. The notation, given a function f of x over an interval a, b in n subintervals, we let x sub 0 equal the leftmost endpoint, so we'll call that one x sub 0, my first x. And then I'm going to call my last x, or the right endpoint, be x sub n. And we're going to call delta x b minus a over n. So we're going to divide this into n subintervals, and the width of each of these is the difference between b and a divided by how many rectangles that we choose to use. So this is the width is equal to b minus a over n. And we call that delta x, or the change in x. Right, so the notation, actually I'm going to write this again right here. I'm going to write my number line. So let's suppose we're looking over the interval from a to b. We're going to call my first endpoint x sub 0, my last endpoint x sub n. So we have stuff going on up here. We're breaking it up into however many subintervals. So if this is my first, and my left endpoint is x sub 0, my first tick mark we call x sub 1. My second tick mark we call x sub 2. Third will be x sub 3, all the way up to, well, this is the nth one. This is the one before the nth one, which is n minus 1. So I am putting this for a reason. The left sum is determined by the width of each rectangle. Okay, you can see that. The width of each rectangle is delta x. And the height of the first rectangle is determined by using the leftmost endpoint. So the function evaluated at the leftmost endpoint. Then the second rectangle is the width of the second rectangle times the height at the next point, x sub 1. And then it's going to be the width of the third one times the height determined at the left endpoint. We're going to continue in this process till we get to the very last subinterval. And the very last subinterval, this width is still delta x, and the height is determined by the left point of the last interval, which would be the function defined at x sub n minus 1. So we never use b when we're determining the left sum. Right. In math, when we have this long collection that's a sum, we abbreviate it with delta notation, or I'm sorry, sigma notation. So sigma is the Greek letter we use for sum in math. So notice these each have a delta x. Then they each have a function evaluated at some point, but that point changes as we move to the right. So we use the sub I notation. We say I starts at 0, and we go to the all but the next to the last endpoint. So this would be the mathematical version of how we would express a left sum. How we would express the right sum, well, we're on the same number line, except over the first interval, the height of the first rectangle is determined by the right endpoint. The height of the second interval is determined by the second endpoint. So the first rectangle is delta x, f, x sub 1. So when we're creating a right sum, we don't use a, or the leftmost endpoint. So it'd be delta x, f of x sub 2, plus delta x, f of x sub 3, plus, and we're going to continue. And this time we go all the way, our very last interval, we'll use the right endpoint, which will be b. So f of, and we're going to call b x sub n, just for consistency. And then we're going to use our delta notation. I equals, well, this time we have delta x, and we're putting in different values of the function, but we're not starting at the left endpoint this time. We're going to start at the one right next to it. So we're going to start with 1 and go all the way to the rightmost endpoint. So this is just a formality. We definitely talk a lot more in detail about this in Calc 2. What I'd like you to do is be able to, given a function, you should be able to divide it into the appropriate number of intervals, create a left sum and a right sum, and perhaps a midpoint sum, and see how they behave. And then just try to get a little feeling for this notation. All right, so the actual area under the curve, so this is how we would express the left sum and the right sum with n subintervals. So what we're going to do is create infinitely many intervals to find the actual area under the curve. So the actual area under a function over an interval is the limit as n goes to infinity of the left sums That's the left sum. And if we were to do the infinitely many right sums, we'll see that these areas will actually converge onto each other. Right there. All right, so to do, read 5.1, exercises 1, 3, 5, 13, and 15. All right, hope everyone's doing good. Talk to you soon.